Good morning, everyone, and welcome to EDP and Applied Matematica seminar. It's a pleasure for me to open session 101 of this seminar. Today we have two excellent speakers, Kais Ammari and William Sindra. Introducing Kais Ammari, we have to Professor Anna Dubova. Thank you, Anna. You can start.
Okay, thank you very much, Juan. Thank you very much, Professor Ammari, to accept the invitation. I'll say just some words for your presentation. So, Kais Ammari is a full professor at the University of Monastir in Tunis. His main research interests are control and stabilization theory related to partial differential equations. He is a holder of the Excellence Research Chair, Jean d'Alembert of Paris-Saclay in 2016-2017. Among his responsibilities, he has been the organizer of more than 21 conferences. He is a founder member of the Mediterranean Institute for the Mathematical Sciences. He is a head and founder of Research Laboratory Analysis and Control of Partial Differential Equation of University of Monastir in Tunis. He has been the header of more than 20 scientific projects and supervisors of 21 PhD theses. He has more than 110 published paper and 4 books for researcher. So today he will speak about the stability of abstract thermoelastic delayed system. So thank you very much. You can start.
Thank you, Anna, for this nice introduction. Thank you, Diego, for the invitation. Hello, everyone. My presentation is about stability or abstract thermoelastic delayed systems, which is based on joint works with Serge Niquez from Valenciennes in France and Cristina Pinotti from L'Aquila in Italy, and Makram Salhi and Farhat Shal from Sfax in Tunisia. Okay. So before getting into details, I'm going to give a short outline of my presentation. So I'm going to start by explaining the motivation behind the work. I will introduce you to take problem as well as the idea and the strategy necessary to solve the problem. Then I will tackle the topic of stability of some retarded abstract wave equation with Kelvin void damping. I will start by showing you some existence results. After that, I will give a spectral analysis for discrete and continuous spectrum. And needed to determine the asymptotic behavior, and I will end the second part by giving an application to the stabilization of the wave equation with delay and the Kelvin void damping. And the third part of my talk, my presentation, I will discuss the stability of abstract thermoelastic delayed system, and is this main part of my talk. Last but not least, I will end my presentation by giving some references I use it. Now, starting by introducing the problem, it's well known that delay equations, like the simplest one of parabolic or hyperbolic equations, are not well posed here is in the sense of Adamar, means that the instability is given in the sense that there is a sequence of initial data remaining bounded, while the corresponding solutions at a fixed time go to infinity in an exponential manner. And according to some works of Raquet and his collaborators. More precise, the same phenomenon of instability is given for more general class of problem of type of this type. For example, for n is equal to 1, you see that is the heat equation, retarded heat equation for n is equal to 2 is just the equation, retarded equation. And in particular, the circular alpha beta system with delay, which given by some couplet system with the elastic one and the heat date one, and the delay is in the elastic or in the heat component. Here, the operator A being a self-adjoint operator in some Hilbert space H, having a countable complete orthonormal system of eigenfunction phi j with corresponding eigenvalues, lambda j strictly positive and goes to infinity as j goes to infinity. We see here that the thermoelastic plate equation appear with alpha beta is equal to 1/2 and A is just the Laplacian operator. And it was shown that we have a strong smoothing property for parameters alpha beta in the region like this in the set and illustrated in the figure here without delay. And for the same system but with delay, the delay is not for the alpha beta system with delay is not well posed in the sense of Adamar in the following region in the set of alpha beta in the interval between 0 and 1 and satisfy some condition and is illustrated by in this figure. A similar result will hold for the related system for where here the delay acts in the heat component and the region of instability is given by the following set, which is illustrated here by the in this figure. And now the question is sorry. So the question is now how to restore existence in the sense of Hadamard and uniqueness, as well as uniform and non-uniform stability. Indeed, we will look in the literature how to treat delay systems. So we begin by give you the first model of system with delay. With delay is given by the following by this term equipped with some initial data and some delay condition here where t is between 1 tau and 0, where tau is just the time delay. And here this model is the typical model of delay system since the first works of Datko and his collaborators on the effect of the small delay. Donc, so we can therefore correct by adding some term like this, which is proportional with the delay term with alpha 1, alpha 2, two parameters, which we take alpha 1 bigger than strictly alpha 2. And in this manner, we can by adding this correction term, it's just a damping term. Alpha 1 is strictly positive and is a positive operator here, and is just a damping term for the free evaluation, and here the delay term. And so we can restore the existence and the uniqueness of the solution, and we can characterize the stability, uniform or no uniform stability for this problem, for this with delay, by for example observability estimates for alpha 1 is alpha 1 and alpha 2 equal to 0 for the free part of the equation of the system. No delay and no damping. We can also correct by a damping term, but not proportional. But you can see here that the correction term here is a term proportion is comparable to this one, with the same operator, but you keep here alpha 1, alpha 2, such that this condition is satisfied, and you can restore the existence of the uniqueness and the stability uniform or non-uniform. But in this condition, but in this situation, the delay is inside omega, and the damping is on the boundary. So the two operators are not proportional and not comparable. So we can also here correct by damping term, not proportional to the delay term, and we can show, for example, for this particular system, and we can prove that the system is well posed on the classical energy space, and that the energy goes to zero by exponential rate for any regular solution, and so we can find some coefficient here, A and K, such that we have the following exponential result of the energy of the system of the wave equation with delay, internal delay, and the boundary dissipation. Okay. Now, the opposite problem means that we have here a dissipation term and here a retarder term or delay term. So the contrast of the effect of time delay on the boundary condition with a velocity term and the wave equation is still, as far as we know, open for the high dimension, and it seems to be much harder to deal with. However, there is one positive answer given by Detko-Laniez and the police, and the one-dimension case for the Coulomb problem, one-dimension problem. Here we have that the damping is inside internal damping, and the delay term is at the boundary in point x is equal to 1, and we can prove that with some careful spectral analysis that that we have the exponential stability for the energy, corresponding energy of this previous problem, where K satisfy this condition in function of A. A is just this coefficient under the damping term, and K the delay term. Okay. But in fact, we can use the delay to stabilize if it is well prepared. More precisely, we can stabilize by switching time delay. And here, for example, T0 is just tau. Tau is the time delay. Or here is just, for example, the observability time or the control time, optimal one. And we consider the free ovulation is here for the interval 0 T0, and after we add some dissipation like this and some delay time. And we can prove that the system is well posed in the energy space, in the corresponding energy space, and stable. I will give you two examples: pointwise stabilization and boundary stabilization. For the first boundary stabilization, we consider the wave equation in 0L times 0 to L. Donc T0 is equal to L. Is it exactly the optimal observability time for the string equation, where the interval is of length equal to L, just is, and the decay and the rate of propagation here is equal to 1, so T0 is equal to 2L. So we add here some retarded term with some parameter A, and we can prove that. I'm sorry, for boundary stabilization, we done something like that, something like previous, the system, and on the boundary, we as this problem, we add some dissipation here from this interval, and some delay terms here. And we can prove that, for example, for the first problem, the pointwise stabilization by switching time delay equal to 2L, and for this choice of the point where the control acts in the middle of the string, therefore any A between -2, 0, we have that the energy is exponentially stable, where the constant C1 depends on the initial data, and L and C2 depends only on the length of the interval L and on the parameter on the coefficient A. And for the boundary problem, by using the stabilization by switching time delay, and we can calibrate mu1, mu2 as following, and we can prove that the solution of this problem satisfies the following exponential stability result, where the energy is given or are given by the following expression, and the H, the Hilbert space of reference, is given by this set or this space. So now, to converge to the and to the solution, to give some solution, to give some solution for the problem. Given in this presentation, we consider the stability of an abstractive equation with delay and Kelvin void damping. Here we consider a scalar equation as the thermoelastic one. For example, just is the first equation or of the previous one of elastic type, elastic one component, or of the heat component. So here we can restitute the well-saidness, the existence and the uniqueness of this problem and the stability by here we propose to add something like as previous the Kelvin void damping term, so something like this. It's the same operator with some parameter for calibration and with the U prime. It's just a Kelvin void damping type for this equation, this type of system. And so we can prove that we can restore the stabilization, or the stabilization is performed using here frequency domain approach combined with a precise spectral analysis. So, here in this section, the main is to study the internal stabilization of delayed abstractive equation by adding this term. Okay. More precisely, given a constant time delay, tau strictly positive, we consider the system given by the following. Here we add just the correction to restore the existence and the uniqueness and the stability exponential. Here, the parameter is strictly positive. B is a linear unbounded operator from Hilbert space H1 into another Hilbert space H, equipped with the respective norms and inner products, and B star is just the adjoint of B. The initial data belongs to some suitable space, energy space. And we suppose that the operator B star satisfies the following coercivity assumption, the inequality given by 31. And we set V, the domain of B star, and we assume that it is closed when the norm V is given by this definition, and it's compactly embedded into H. And so now we introduce the auxiliary variable Z is equal to B star U T minus tau, rho is the variable between 0 and T strictly positive, and the problem is now equivalent to the following. The first equation is just we take rho is equal to 1, and is just this term. So we have the same equation by this auxiliary variable, and with this second equation is just a transport equation and some initial condition and boundary condition. And so the idea is here we can reformulate or rewritten the first problem, the initial problem, as a abstract Cauchy problem, like this, something like this, and with A is just the operator given by this expression with the domain of A, domain of B star, times the domain of B star, H1, 0, 1 with values in H1 and some compatibility condition in the Hilbert space, which is augmented the classical or the natural Hilbert space with L2, 0, 1, H1 with the standard inner product given by this formula. Where key here is she is strictly positive, is a parameter fixed later on. Okay. And we will show that A generates C0 semigroup on H by proving that A, the shifted operator is anticipative for an appropriate choice of the constant C and in function of the parameter tau A and she. If she is strictly bigger 2 tau divided by A, then there exists A star such that A minus A star minus 1 identity is anticipative in H. Okay, so we have the following. We restore here the system, the existence and the uniqueness of the first problem without the Kelvin void damping. And the system now is well posed. More precisely, for every initial data in H, there exists new solution continues on time with values in H. Moreover, if the initial condition are or is more regular in the domain of A, then we have that the solution is continuous on time, values in domain of A, and C1 on time values in H. And we can keep V is equal to U prime, and U is the solution of the initial problem. Now is well posed in this space H or on the domain of A. And now for the stability, for the stability of this problem, the uniform stability, exponential stability, we need some spectral analysis. So here the domain as the domain of B star is compactly embedded into H, the operator B star has a compact resolvent. Hence, let lambda k be the set of eigenvalues of B star repeated according to their multiplicity here, and denoted by phi k, the corresponding eigenvectors that form an orthogonal basis of H. And so, if tau now is less than A or equal, then any eigenvalue lambda of A satisfies the real of lambda is strictly positive. Is strictly negative. Okay, and in the sense, if A is less than strictly tau, we show that there exists some pairs of A tau for which the system, both system becomes unstable. Hence, the condition tau less than A is optimal for the stability of this system. Means that there exist pairs of A tau such that A is strictly positive, strictly less than tau, and for which the associated operator A has a pure imaginary eigenvalue. So here you have some continuous and discrete part of the spectrum. So you should prove that the spectra is included on this part of the complex plane. So sigma is just the continuous one, continuous part of the essential or continuous part of the spectra of A. So it holds that sigma 1 is equal to discrete and continuous one. And for tau less than A, sigma 1 is just on the right part of the complex field. So we have the asymptotic stability of the energy of this problem of the system with the damping, with the Kelvin damping dissipation, and where tau is less or equal to A, or A is more than tau. Tau is an arbitrary delay fixed strictly positive. So now for the uniform stability, I'm sorry, we show that if tau is less than A and T and Xi, so I'm sorry, bigger than the 2 tau divided by A, the semigroup decays to the new steady state with an exponential minor decay rate. Okay, so we have the following result of exponential or uniform stability under this condition, and someone Xi is just a parameter. You can choose something like this one plus one, okay, and A is bigger than or equal to. So here we can consider the case where A is equal to 10. Okay, for this, to obtain this, our technique is based on a frequency domain approach and combines contradiction argument to carry out a special analysis of the reservoir. We will employ the following frequency domain theorem for uniform stability of C0 semigroup in a Hilbert space, in a classical manner to prove exponential stability or uniform stability for semigroup operators. So according to Hang and Push, we just use this length. Two conditions satisfied. First one, real of spectra strictly negative, and we have some uniform estimation for the resolvent here, real of lambda positive or equal to 0. Okay. And now I give you an direct application of this result. We can consider the equation with this by adding this term with A and with some directly condition on the boundary and this delay condition given by the gradient. Okay, here the Laplacian is the gradient, and so B star is given by this operator. So this operator introduces in our abstract framework, of course, with H is equal to L2 and V minus divergence. Domain of B is just H1 of omega with values in L2, and B star is just the gradient operator, and the domain of B star is just H1 0 of omega. And so the operator A is given by following with domain, and the vector space H is just this one. And we have as directly consequence of the main theorem in this part of the presentation here, that if we take A bigger than tau, and she bigger than 2 tau divided by A with this energy. This the natural one plus delay one. I'm sorry, and we have this exponential stability result for all initial data in the domain of A. And now we converge to the main part of this presentation, where I will tell you about stability of abstract thermoelastic delayed system. More precisely here, H we consider H be a Hilbert space equipped with an inner product and inner A is just a self-adjoint strictly positive unbounded operator and alpha beta in 0, 1, the interval 0, 1. And we consider the following two Cauchy problems modeled respectively by the two abstract thermoelastic systems with delay given by. For the first one, we add this correction, and with the second one, this one. Okay. So now here we are interested in the way to restore the existence and the inequality of these systems, and the study and to study the asymptotic behavior of solutions, of corresponding solution. So for beta alpha in the region 2, given by the set, and which is illustrated in this figure. And it's well known that alpha beta system without delay with A is equal to 0, so is equal to 0, is well posed, and the whole region 0, 1 times 0, 1. And by and Koja and his collaborators identified the region of exponential stability to be given by this set, S. Afterwards, Ao and Liu give a classification of the regions of stability and instability of the system without delay and without dissipation, damping. Here, the region of stability and the region of instability, no delay and no damping here. And they showed that the region of polynomial stability is given by S1, S2, S1, S2, this region, okay, S3, and this region is just this set from this region, this one. Is given by R, and the region of instability is given by S3, is here. And note that the region of stability is then Q is just S and now for the first one, we define U, capital U, as U prime theta and Z, the same auxiliary variable as previous. And so the first problem can be formulated as a first order system of the form of the Cauchy one, not a Cauchy abstract problem, where alpha beta is given by this definition with domain, and the Hilbert space is just this one with inner product or scalar product given by where here she is just 2 tau divided by A as previous. So we have that the first problem now is well posed, and we have that for beta alpha and Q, A bigger than tau, the first system is well posed on the energy space. More precisely, the operator A alpha beta generates a C0 semigroup in H. As for every initial data in H, there exists a new solution continues on time values in H. And moreover, if the initial data is more regular in the domain of A alpha beta, then we have that the solution is more regular than continuous in time in the values in domain of A alpha beta and C1 in time values in H. And for the stability for all beta alpha in the set Q and A bigger than or equal to tau, the system, the first system is exponentially stable. So by adding this term, we can restore the existence inequals and exponential stability under the same condition as above. And for beta alpha on this set. And we give you an application, direct application for this for that theorem for the thermoelastic plate with delay. We consider here the system with alpha is equal to beta is equal to 1/2. H is just L2 of omega, which is smooth open bounded domain in Rn, and consider the following problem where tau and A are real positive constants. Here, the square of A is just minus Laplacian with domain H10 and H2 and H2, and A is minus B Laplacian with this domain. We can identify the operator alpha beta is equal to 1/2, the domain, the space H, the Hilbert space, and we have the following stability theorem, stability result. We have for all A larger than tau, large or equal to tau. We have the exponential stability for all initial data in the domain of the operator. Now for the second one, as the first, we can be formulated as a first order system, Cauchy problem, with A alpha beta, where alpha beta is given by this expression with domain, and we identify the Hilbert space with a scalar product here, but here we have some parameter strictly positive, and we have that the second problem with by adding this term is well posed. We have existence and the uniqueness in the energy space. More precisely, if we suppose that beta alpha and Q assume that A bigger than kappa, and the parameter in this interval, then the system is the second system now is well posed. More precisely, the operator generates a C0 semigroup of contractions in H, and for that's for every initial data in H that exists in your solution, the classical space, the classical regularity space, and for initial data more regular, we have that solution is then more regular. And for the stability, and for stability, now we should suppose that A is strictly bigger than kappa, and the parameter chi is in the open interval. Then the semigroup is exponentially stable, but in the region S. by specifying the regions S1 and S2 as follows. S1 is given by this one, S2, S1, S2, which is illustrated here by in this figure, S1 and S2. We have the following. Assume that A bigger than kappa. The same thing for Xi. The semigroup has the following stability properties. In S1, we have some polynomial stability of order of this order. In S2, the same thing, but for different order, in function of alpha, beta, in S1 here and in S2 here. And an application of this abstract theorem for a thermoelastic beam, we consider the one-dimension delayed thermoelastic beam model in an interval 0L as strictly positive, something like this. A is just the Laplacian with this domain, and alpha beta is 1/2, and alpha is just square of A, which is more Laplacian with this domain. We can identify the operator A 1/2, 1/2, which is given by this formula and the domain and the Hilbert space. And we have that in this condition, under these conditions, the system is exponentially stable. And at the end, I give you some reference directly linked with my talk.
Okay, thank you.
And thank you for your attention.
Thank you very much for your nice talk. So now we have time for some short questions because we are a little bit out of time. So, but you can use your microphone and also use the chat. So are there any questions or comments?
I have one. May I ask a question?
Yeah, sure.
Hello, Kais. Thank you very much for your talk. It was very good. Okay. Just a curiosity, because you have a result with some delay, right? And
Yeah.
what about if you have some other kinds of non-local effect, like memory terms? Can you obtain similar results, or?
Yeah, I think, but I think because here the delay is punctual, pointwise delay from discrete kind of delay.
Yeah.
But for the memory term, it just continues. Donc ça I think I don't. Donc ça I think that that you can done like this. You can prove prove the existence in sequence and study the stability by using frequency domain approach.
Okay.
I think.
Okay, thank you. Thank you very much.
I have a quick question, please.
Sure.
First of all, thank you so much, Professor, for this nice talk. A similar question, honestly. What do you think of adding non-linear dampers and dampers instead of linear ones, and changing the abstract problem into adding plus a capital F of U? And what do you think about the dynamics of such a problem? I mean, in the sense of attractors.
I think you can done. You can done because if the linearized system is stable. Is stable. So you can then and you can prove the nonlinear by adding some nonlinear dissipation. You can restore the existence and the inequality and the stability, of course, because the damping can be restored and can be controlled the delay term, linear or non-linear.
So one can obtain similar result for stability, even though if the nonlinearity is
by using linear part by using linearization by using linearization approach or techniques. You can stabilize the nonlinear problem by linear one, by linearized one.
Yes. Thank you so much.
Thank you.
Okay, thank you very much. Are there other questions? So if not, we thank the speaker again. We are a little bit out of time. So thank you, Kais, for being with us.
Thank you.
Okay.
Thank you, Anna. Thank you a lot, Professor Ammari, for your excellent talk.
Thank you.